What we'll do today, we'll go through problem solving of questions from the review problems of Chapter 7 and from Chapter 8. So you have a copy of the review in Chapter 7. What I'll do, I'll select some questions from 7. So if you show it on the camera, review problem Chapter 7, first page. What do you see on the first page? Question 1, 2, 3. These are just questions about how to use dot product. If you have vector A dot vector B, what we learned early on during the course. So finding the angle between two vectors, yeah? How to do dot product. Which one? Okay. So question 1, 2, 3, it's just a practice on this. So if we go to the second page, you have 4, 5, 6, and 7. Now if we look at question number 6. Question number 6. What does it say, question number 6? A 5-kilogram object is pulled along a horizontal surface at a constant speed by a force of 15 Newton. So question 6, we have a force, 15 Newton, acting at 30 degrees. What is the work done by this object when it moves 6 meters? So this is the question. So this is about Chapter 7. Work and energy. Now, what's the question? You have a force applied on an object and the force at 30 degrees and moves it 6 meters along a horizontal surface. So if this is the object, maybe this is the force F, angle theta, moves it from here to there. 6 meters. The question is, how much work is done by this force? To find work, we need the force magnitude, displacement magnitude, cosine, the angle between them. Here, magnitude, 15. Displacement, 6 meters. Cosine, 30. It gives you the work in joules. So this is just a warm-up question, standard question. How to apply force, displacement, and cosine, the angle between them. Now the next question, question 7. Some of the questions I just give you the idea how to do them, yeah? Not solving them. Like question 7. Look at question 7. A single force acting on 5 kilogram mass. So we have a single force on mass 5 kilogram object in such a way that the position of the object as a function of time is this. X equal 10t minus 5t squared. X is meter in meters, t in second. The question is find the work done to move the object from time 0 to time 4. We need the work from 0 time to 4 seconds. Okay? We need the work. So, what we have to do here? If you want work, always start from the question. If you want work, what do you need? Force and displacement and the angle between them. In this question, it says, how many forces do we have? One force. Single force. Which means the force you have here is F net. F net. So if you have F net and you have displacement, what's the angle between F net and displacement? 0. You know the angle. When you have F net, the angle between F net and the displacement is always 0, moving in the same direction. So what I need here to do, I say WF equal F delta R or X, doesn't matter, cosine 0, because this is F net, W net. Do I have the force? No. This is a review question. What is given? Position as a function of? What can you do to this one? Differentiation. How many times?
2 times.
We'll get what? So x, when you derive it twice, it gives you a. Second derivative of position with time is acceleration. Okay. If you have acceleration and mass, you get what? Which force? F net. Yes? So just multiply m by a, it gives you F net. And if you know F net, yes? What else you need now? Displacement. But here it's not delta R, it's x only, so it's delta x. What does it mean, delta x? X final minus? X initial means x at 0 time, which means evaluate this at, it gives you x1. X at 4, x final, yes? So if you know x final and x initial, you find, and then substitute here, you get the work, yes? So this was a review question, linking the previous with the present. So this was question 7. Review problems. Now let's take, I'm selecting questions with different ideas. Question 9. Question 9 says a 2 kilogram particle has an initial velocity of 5I minus 4J meter per second. Sometimes later, its velocity is 7I plus 3J. What work was done by the resultant force? What work's done by the resultant force means W net total. During this time interval, assuming no energy is lost in the process. Okay, so I write it down here on the board. Question 9. We have the mass, 2 kilograms. The initial velocity here is given as a vector, 5I minus 4J. Final velocity, 7I, 3J. What's the question? What is the work done by the force here, yeah? But this force here is net. So we want W net. Okay. Now remember, chapter 7 based on a theorem which says W net is always equal to change in kinetic energy. Now on the formula sheets, which I gave you for the final exam, make sure you are familiar with it. Where to find the formulas? On the second page, okay? Just a show. Yeah, let's not show it to the camera. Maybe. On the back, what do you see? Back page here. You see the section for chapter 7 and 8. All the formulas needed in 7 and 8. Now, don't you see W net equal change in kinetic energy? Okay? So make sure you know how to find the formulas here. And of course, the second part is about chapter 15. Chapter 15. And the first page, these are for the previous chapters, like chapter 1, 2, 3, in the same sequence. So this is what you'll get in the formula sheet. Anyway, so what we have here, W net is change in kinetic energy. So if you want W net, how do you find it? By knowing the change in kinetic energy. What is change in kinetic energy? half m v final square minus half m v initial square. Do you have the mass? Yes. No. Now we come to v final. This is v final, yeah? But remember, energy is a scalar, not a vector. This is a vector. You need the magnitude of the vector. What's the magnitude of v1 and v2? v1 magnitude, or v2 magnitude here, v final magnitude is the square root 7 square plus v initial 5 square plus 4 square, yeah? So the idea of this question is that when it comes to v initial, v final, and you have the vectors, evaluate the vector, the magnitude, and substitute. You put a value here and value there, and you find change in kinetic energy, which is equal to W net. So this is the idea of question 9. Now we move to question 10. Question 10 says, a force of 2I plus 3J. So we have a force, 2I plus 3J, in Newton, of course. Act on 4 kilogram mass. So the mass is 4 kilogram. And it moves it from point 2I plus 4J in meters to a point 3I plus 5J meter. The question is, how much work is done by this force during this displacement? Find the work of F. All right? Let's see how we can do this. Now, to find work, again, you need 3 things. The force magnitude, displacement, cosine the angle between the force and displacement. That's one way, if you are dealing with magnitudes. If you are dealing with vectors, you need 2 things. The force vector and displacement vector. And you do dot product. In this question, it's easy to use the magnitudes or the vectors. Vectors, because the angle is not known. So what do you need? You have to say WF is force vector dot displacement vector. Okay. Now, this is a point. This is another. And you move the object from this point to that point. Yeah? So it's like this. Initially it's here. Finally it's here maybe. So what does this represent? Initial position vector. R1 vector. Not x1. X if you don't have j. Here we have I and space. And the second point. So if you know R2 and R1, can you find delta R or not? Subtract. So delta R, the displacement vector, is R2 minus R1, which is 3 minus 2, I. 5 minus 4, J. Now we know delta R vector. Can we do the dot now? F 2I 3J dot I plus J. When you do dot, the I by the I, but no I. 2 by 1. The J by the J plus 3 by. So what's the answer? 5 joules. 5 joules. So this is how you use dot product to find work. F dot delta R. Question 11, it's the same as question 10, question 11. The only difference is that it's in 3 dimensions. So if you have the sheet, you have the sheet. What we have, a constant, a force, again, a constant force of 15 Newton in the negative y direction acts on a particle as it moves from origin to a point 3I plus 3J minus K. How much work is done by the given force during this displacement? So in this question, the force is 15 Newton. This is magnitude, yeah? But which way? Negative y. Now, if I want to write this force as a vector now, this is magnitude. How do I write it? F vector is minus 15J. Yeah? If it was negative x, positive y, 15J. Yeah? So you have to know. So the force vector is ready. Now, the question says it moves from origin. So what is the starting point? So R1 vector is 0. To a new point. What is the new point R2? 3I, 3J, minus K. Eh? So how do you find the work done by F? What do you need? Force, displacement, cosine the angle. That's if you are dealing with magnitudes. Now here, do you know the angle between F and delta R? No, so it's better you use what? Vectors. So what do you say? W is F dot delta R. Now, how much is delta R? Same as R2, yes? So delta R here is R2 minus 0, which is R2. So now you just have to do a dot product between F and R2. How much is the I here? 0. By 3, 0. J minus 15 by what? By 3. And the last one? 0. And the first one? 0. So it's minus 45 joule. This is the work done by the force. Now, 13, question 13. Question 13 says, if the resultant force acting on 3 kilogram object is equal to 3I plus 4J. So we have a force equal to 3I plus 4J. What is the change in kinetic energy? Find delta K. As the object moves from 7I minus 8J meters to 11I minus 5J meters. That's, yeah? So what is the change in kinetic energy? Right. Remember the central equation? W net equal to the change in kinetic energy. That's W net, which means W for F net. In this question, this F is resultant force or not? So this is F net. So if I do dot product between F net and displacement, I get W net. So this question, to answer that, you need to find W net. And then W net is equal to the change in the kinetic energy. So this question is either find W net or find delta K. It's the same. How you find W net? You need dot product, yes? But is delta R ready? No. This is R2. This is? So subtract them to find delta R, yeah? Which means 11I minus 5J minus 7I 8J. Yeah? 11 minus 7 minus 5 minus minus is plus, yeah? Minus 5 plus 3. Now do dot product. 3 by 4, 12. 4 by 3, another 12. 24 joules. This is W net. But W net is? So it's the same. Right. Now we take a new approach to solve the problems. Question 14. Question 14. A force of 5.4 Newton is used to push a block across a rough. Rough means there's friction. Horizontal surface, and the surface is horizontal. So we have a force F has a value of 5.4 Newton, pushes on a rough. The magnitude of the force of friction, which means Fr, between A and B is 1.2 Newton. The friction force is given. And this is between point A and B, from A to B. From A to B, the distance is 0.5 meters. They are 0.5 meters apart, the 2 points. Now, if the kinetic energy of the block at A, kinetic at A, is 4 joules, and the kinetic at B, 5.6 joules, answer the following. First part. What is the work done by the force to take it from point A to point B? Part B, what is the work done by friction force, WFR? So this is the question, and there is a drawing. I'll do it here. This is F, and this angle, theta. And this is point A, and this is point B. Right. In this type of questions, we do not need to use vectors. Why? Because the object on the surface, we are interested in the magnitudes. The direction is either to the left or to the right, the motion. No other directions. So what we should do here to answer the question, first of all, you need a free body diagram, just to show all the forces. This force is pointing to the object, so is it appropriate, or I have to shift it? Shift it to the other side. So the new drawing, if I want to do it here, I have F this way. This is point A. This is point B. And this angle theta is with X, yeah? So here it's with X as well. What are the other forces on the question? Friction. If you are pushing this way, definitely is this way, yeah? Fr. And normal and gravity force. That's it. These are the 4 forces in the question. Now, what do I want? Work done by? Only. Okay. The normal procedure, you need the force, displacement, cosine the angle between them. Let's see if we have all these. If I want to find WF, I need F. And here is delta X because you're moving on X, yeah? And cosine the angle between them. I'll put alpha just in case it's not the same. Do I have F? Do I have delta X? Between A and B is 0.5. Do I know the angle between F and delta X? No, not given. It's called theta, but it's not given. But 6 minus what? I know, but how much is it? You don't have the value. This angle theta is unknown. So I can call it here theta as well, same. This is the direction of F. Where is the direction of delta X? So this is the angle between displacement and F, unknown. So can I answer the question this way? No, dead end. You have to change the technique. You go back to W net. What does it mean, W net? Total work. Yes? Now, when you say total work, it means work of all the forces. How many forces do we have here? 4. But remember, N doesn't have work. FG doesn't have work, because it's at 90 degrees to the motion, yes? So W net in this question is just WFR plus WF, yes? Because W normal is 0. WF is 0 because of the angle 90 degrees, yes? You're moving this way, N is that way, and FG that way, 90 degrees. By the way, when you answer questions on work, when you do the free body diagram, you don't have to put the component unless you need them, yeah? Because you deal with the force, not with the components to find W. Yeah? You can put the component, but use the original force to calculate. So, can you see the other way now? I couldn't do WF that way, so I have to do it this way, which means now this is unknown. So I have to know W net and W friction. How do we find W net? From the theorem. Changing kinetic? Okay. Do I have the changing kinetic energy? Yes, I have Ka and K. So how much is Kb minus Ka? It's 5.6 minus 4, 1.6 joules. So now W net is known, 1.6. What is left? W friction. If I calculate W friction, I know WF. So how do you find W friction? 180 minus FR delta X, yeah? Cosine 180 minus, yeah? So there's no need to put. Is FR given in the question? Yes, 1.2. Displacement, 0.5 meter, yeah? So here you find the work done by 0.6, yeah? Joules. So now this is minus 0.6 joules plus, then you can find WF. WF, 1.6 plus 0.6 now, 2.2 joules. So this is the answer for part A, work done by applied force. Which means now you should know that there is another way to answer questions about work done by forces. How? Find the total work and find the work of the rest of the forces. You find the missing work. And instead of knowing the force, displacement, cosine, the angle. The second one, we already answered it. Yeah? What is the work done by? Friction. Minus 1.6. So it's answered already. Next question. Now, if you look at question 15, question 16, question 17, they all about graphical representation of force with displacement, force with position, sorry. So 15, 16, 17. 18, it's not force with position, it's kinetic energy with position. All right? So if we go back to 15 now, 15, question 15. Fifteen says, the force on a 3 kilogram object as a function of position is shown in the figure. If an object is moving at 2.5 meters per second when x is 2 meters. So I have a speed 2.5 meters per second at x equal 2 meters. What is the speed, v, when x is 8 meters? Of course, the mass is 3 kilograms, and this is question 15. Right. This is the standard way of solving this question. Whenever you have force with position graph, what is the first thing you can calculate? How? Area under the graph. So each time you see force with position, like this question now, something like that. Newton meters. I just put a rough scale. This point is 4, this point 1, this point 3, and this is 8, 9. Now, what's the question? Find the work done from 2 to where? Oh, sorry, not the work. Find the speed at 8 here. Here, at 8, x equal 8. What is v at 8? What's the speed at 8? Okay. Now, if I have a graph of f with position, the only thing I can do first is to find the area under, and the area of the graph gives you W, work. How many forces do I have here? One force. So this is F net. Huh? Single force. So if I calculate the area from 2, because start at 2 here, to 8, this area. What does this area represent? W net. Now, can we calculate this area? Easy, yes. From the scale, you find each square is 1 joule, yeah? So if you count them, you have 6 here, up to here 6, and this is half. Or if you want to look at it as shapes, a triangle with a long rectangle, 2 shapes, add them. So the area here, W net, equal area, and it's equal to 6.5 joules. If you know W net, can you answer questions about kinetic energies, velocities? Yes. So W net equal kinetic final minus kinetic. Okay. Initial speed at 2, yes, because you did this area from 2 to 8 meters. So initially at 2. What's the speed? 2.5. So I can replace this with half mv initial square, and this one half mv final square. What is the mass? 3 kilograms. So this is a 3. Final velocity unknown. Initial velocity 2 point. And you find the, and W net 6.5. You find the unknown final velocity. So it's a standard question. In the graphs, you can calculate W net. You can calculate kinetic energy, initial or final. You can calculate initial velocity or final velocity. All to do with W net equal change in kinetic energy. So this was question 15, yeah? So this is a sample. Now let's move to question 20. Question 20, another type of question. Question 20 says, a force acting on an object moving along the x-axis is given by F sub x equal 14x minus 3x squared. So the force here is a function, 14x minus 3x squared. How much work is done by this force? Find the work done by this force, WF. As it moves from x equal minus 1, so from position x equal minus 1 to position x equal plus 2 meters. Right. Okay. Now, what's so special about this question? This time the force given constant or variable? Variable. So if the force is variable, how do you calculate work? What you have to do? Integration. This is question 20. We know that work equal integration of force from x1 to x2. Initial position to final position. Anytime you have a variable force and you want to find the work done, just do integration. So now I have to integrate this force. What's the integration here if I substitute? Integration of 14x, 3x squared, all dx. Now the dx will be on both. And x1 is minus 1, x2 plus 2. What's the integration of 14x? 14x squared over 2 minus. Second one, 3x cubed over from minus 1 to plus 2. 14 over 2, 7. 3 with the 3 cancel. From minus 1 to 2. This will give you W. What's next? Upper minus lower. So 7, 2 square minus 2 cube. This is upper minus lower. 7 minus 1 square minus 1 cube. And you evaluate the value, function. Right, just be careful when you evaluate. Here you have minus 1 cube. Minus 1. Multiply by minus, plus. Here you have minus 1 square becomes a plus. And then you have a minus outside. So be careful when you substitute the values. Don't get it wrong. I leave it to you to finish the calculation. So this was an example of variables. Now, in page 6, question 21, question 22, 23, 24, 25, all of them about a spring is being moving horizontally. A standard question. So I'll choose question 21. A 10 kilogram block on a horizontal frictionless surface. Do we have friction? No, frictionless. Is attached to a light spring. Light spring means the mass of the spring is negligible, nearly zero, very light spring. Having a spring constant of 0.8 kilonewton per meter. 0.8 kilonewton per meter. Be careful with this unit. It's not a Newton per meter, kilonewton. So you have to change it to Newton. Okay. The block is initially at rest. What does that mean, initially at rest? It means not in motion. Velocity initial is 0. It's not just that. The block is initially at rest and at its equilibrium position. It means that the spring is not stretched, compressed. Equilibrium. When a force of 80 Newton, this is when you apply a force of 80 Newton parallel to the surface, you apply it on the block, as shown. What is the speed of the block? Which means what is the final speed, yeah? Initially it was at rest. What is the speed of the block when it is 13 centimeters from the equilibrium position? So how much is being pulled? 13 centimeters. This is x final, final position. Okay. How do we solve these questions? I'll show you the standard procedure, and then you can apply it to all questions of springs. Don't forget, we are still in chapter 7. And the major equation in chapter 7 is what? Remind me. W net equal change in kinetic energy. Don't forget, this is the theorem. If you have a question of a spring, think of this equation always. When we say W net, we mean W of all the forces in the question. Now, if you have a spring, in this question, you have a spring horizontally, and there is an applied force. How many forces do I have?
One.
Friction, this one, because this system in this question is a friction. No friction. Horizontally, I have applied force. Of course, I have spring force as well. This way. And of course, I have Fg and normal. Now, W net, in a question similar to this, generally speaking, comes from three major works, three major forces. The first force is always W of the spring, force of the spring. Spring Fs does work or not? Ws plus applied force Wf plus friction force. Generally, I'm talking, not here, not in this question. General. So whenever you want to solve a question of horizontal spring using the concept of work, remember you have three works in general. Work of the spring force, work of the applied force, work of the friction force. You add them, it gives you W. And what is W? Change in? Now, what you do next? Read the question. If you have an applied force, it means you have the work of force. Keep it. If you don't have an applied force, 0. This is out, yeah? If you have a friction force, then you have a work done by friction. If you don't have friction, out. But Ws, always there because you have a spring. This is all equal to change in? So for our question number 21, yeah? Do we have friction? So this is out. Do we have applied force? Yes, so it stays. Of course, we have a spring. So what is my equation in this question? Ws plus equal kinetic final minus? Okay. Now, in this question, or questions of spring, always make a small table. In this table, you need 4 things. What was the initial position of the spring? What was the final position of the spring, x final? What was the initial velocity of the block? What was the final velocity of the block? Ask yourself these 4 questions and answer and fill. Of course, sometimes you're able to fill 3, sometimes you're able to fill all 4, yes? It depends on the unknown. In this question, 21, it says the block is initially at rest. So, what's the initial velocity? So, Vi is 0. What else? Initially at rest and at its equilibrium position. So, what is the initial position? 0 as well, expo. Now, the question says, what is the speed when it's at 13 centimeters? So x final is unknown when x is 13 over 100. Meters, yeah? Change it to meters. Look. So what is the unknown? Final speed of the block. Of course, the question says kappa. Be careful with kappa. This is not kinetic energy. Kappa is 0.8 kilonewton per meter, which is 800 Newton per, because the kilo is 1,000, multiplied by 1,000. Okay. Now, why do we need the table, this one? Look here. How do you calculate W spring? On the formula sheet. Section, formula sheet. Where do you don't need it. Where do you see the WS? Can you see it? Okay. So if you see it, tell me, what is WS? Half kappa X initial square minus half X final square. This is WS, standard. Plus, how do you find the work of a force? You need the force, delta X, cosine the angle. But in a spring, you apply the force horizontally, so it's always 0. Equal. Kinetic final means half mv final square. Kinetic initial half mv initial square. This is the equation without taking the conditions in consideration. Now look at the table and see. How much is x initial?
0.
So this term becomes what? 0. Because x initial 0. V initial?
0.
So it means this term becomes 0. What is left? This term. This term. And be careful. This is 0 minus, so it's minus. Now substitute. Minus half. Kappa is 800. X final, 13 over 100 square. No, position. F in the question. What was the applied force? 80 newtons. The force given. 80 newtons. So it's 80 newtons. What was the stretching of the spring? 13 over 100. Cosine 0 is 1. Half. The mass of the block, 10 kilograms. The mass was 10 kilograms. So it's 10. And the speed final needed, yeah? And that's 0, yeah? So what is the unknown? V final only. Find it. Okay, now I gave you the standard procedure of how to solve a questions of spring. Just practice. This is your standard equation. You can here put K final minus K initial. And then ask yourself, do you have friction? If yes, leave the work of friction. No, out. You have applied force? Yes, leave it. No, out. But work of spring is always there because it's spring. Equal to change in kinetic energy. Yes.
So if we do F net equals to MA.
Which F net?
F net.
Here?
Yeah.
No, we don't. There's no such a thing F net equal MA here. Because when this one moves, the acceleration is not constant, so it's not easy. We'll come to it in chapter 15, when the spring in motion. Here we just look at it as a normal object. Now, it's dangerous to say F net. How you find F net? You say F minus Fs?
Yeah, no, Fs minus F.
It doesn't matter. No, of course. But Fs, is it constant or variable? Yeah? So you can't have one value for it. So your F net is variable. All right? That's why the acceleration here is not constant, it's variable. Now, the last, by the way, question 25, there's a mistake here, question 25. The block diagram, I did it by mistake, it's a copy-paste, yeah? Doesn't belong to question 25. It's the same as question 21. So just remove it because there's no applied force in question 25. What you can do, just remove the F, wipe the F, so there's no pulling force. if you want to use the diagram. Just correct it. Anyway, now, question 26 and 27. Question 26 and 27. These two questions are about simple pendulum swinging. So I'll look at 26 first. A 0.6 kilogram object is suspended from the ceiling at the end of a 2-meter string. So the length of the pendulum, 2 meters. Now, when pulled to the side and released, when we use the word release something, it means the initial velocity or speed is 0. When you release or drop, initial velocity is 0. It has a speed of 4 meters per second at the lowest point of its path. So this is the speed when it's at the lowest. I'll show it to you on the board. What maximum angle, we need the maximum angle, does the string makes with the vertical as the object swings up? As it swings up, not when it swings down. Right. Before I solve this question, let me show you the pendulum. And remember, we need the pendulum in chapter 15 as well. So make sure you understand the concept here so you can apply it in chapter 15. This is a simple pendulum when it swings like that. Okay? Now, the pendulum usually, we look at 2 points. One of them is always the lowest point here, when it's here. The other is when it makes an angle. Now, it could be this point, or this point, or this point, anywhere, or this point, yeah? So you have always 2 major points. One point is the lowest. Other point when it goes up. Now, what's the shape of the motion? It's an arc, yeah? Circular. But we don't consider it as circular here. Just look at it as you have an arc. So the motion is not in a straight line. It's on an arc. Now, if you have a question of pendulum, you can solve the question or the problem using the technique of chapter 7, which is W net equal change in kinetic. Or you can use the technique of chapter 8, conservation of energy. Which one is easy? Chapter 8, conservation of energy. But what I'll do here, I'll just solve this one for you using chapter 7. And later on, I think it's better to solve it by conservation of energy. So I just explain this just in case you want to apply. Now, this point is the lowest, yeah? At the lowest point, you always have maximum speed, not 0. The second point, it's the maximum, when it reaches maximum angle, so it's 0, stops, or it's still going up, or? So how do I know the second point is maximum or not? From the question. If it says maximum angle, it means here what? The kinetic energy here is 0. But if it's just a normal angle, no, it means it's still in motion, up or? Second way. If I say I pull it sideways, now it's here, yes? And I use the word released. What is the velocity here? So it's maximum as well, yeah? But if I said pull it sideways and pushed it, it means the velocity is 0, or initial velocity, yes? Or here and I pushed it up. Huh? So always pay attention to the second point, not the lowest. The lowest we have velocity, but the second one, sometimes you don't have kinetic energy, sometimes you have, yeah? Right, in our question, it says when this one moves between the lowest point to a point with maximum x, find the maximum theta. Find maximum theta. Let's draw the question. This is the ceiling. This is the pendulum. And the length of the pendulum, L, 2 meters. This is at the lowest point. Now, when it's here, it makes an angle, theta. Don't forget, this looks shorter, yes, but it's the same. This is L. and it swings on an arc. Now, if I say this point is point number 1, and this is point number 2, or initial final, or final initial, it doesn't matter. Stick to the numbers on the diagram. What's the question? What was the question? What is the maximum angle? Theta. We need theta. Theta max. Okay. Now, at the moment, if you want theta, can you use sine, cosine now? No, because you don't have a right angle triangle. So what you have to do, you have to create a right angle triangle. Where is that? From the object, second point, straight to the vertical. Straight. Don't do this silly mistake. This is not a right angle triangle. Straight. So now I have a 90 degree here. Look at this triangle. In this triangle, this side is L, yes? This is theta. Now I have this side up to here, and I have this one. By the way, this side is not needed because we are not having conical pendulum to say this is the radius. But this side is needed. So I'll call this side H. And from here to the lowest, call it Y. Now from the diagram, what is L equal to? Okay, this is one equation. L is H plus Y. Now think of theta. Will you use sine, cosine, or tan? Cosine. Why? Because you have the adjacent and the hypotenuse. So use cosine theta is H over L. So these are the two equations needed, yeah? Keep them. Now back to our question. We want theta, yes? To find theta, what do you need? H and L. L is given or not? So what is not given? Now, to find H, you have to know L and this is Y, yeah? So if you know how much is this Y, you got it. To find this Y, you have to do the equations for work. Okay? Now, I want to apply W net equal change in kinetic energy between 1 and 2. Between 1 and 2. What is W net? Work of all the forces. How many forces do we have here? 2. We have tension force and we have a gravity force. Right. So W net here is W tension force plus W gravity equal kinetic. Now, the question says it's in way down, yes? So where is the initial position? 2. Where's the final? 1. So it's better we swap them. So I'll make this one 1 to say this is the start, and this is 2. To have the same sequence. So this means kinetic 2 minus kinetic 1. How do you find the work of a force? You need the force, displacement, cosine the angle between them. Which way is the FT? This way, eh? Which way is the displacement? Is it on a straight line? On an arc, yes? So where is the angle between FT? It's the angle between FT and the arc here. Yeah? What's the angle between FT and the arc at this point? If you're moving on an arc, at each point on the arc, you are going tangent to the arc, yeah? Like here. If I say the object is here and moving down, at this point, what is the direction? Tangent, yes? So at this point, this is the direction of delta r. But at this point, this is direction of displacement. Yeah? At this point, where is the tension? Perpendicular on the arc. What's the angle between Ft and delta r? Always or sometime? Always, because it's like circle. Yeah? You know that in geometry, this radius and the tangent are always at 90 degree perpendicular. This is the radius, this is the tangent. So at each point on the path, the angle between Ft and the displacement is 90. Cosine 90? 0. So how much is the work done by Ft? 0. Which means, whenever you have a pendulum, the tension force has no work. 0. In pendulum. So what is left? Gravity. Good. Now work of gravity, how do you calculate it? You need force of gravity, displacement, cosine the angle between them. This is Fg here. Which way is delta r? Always tangent. Here, this is Fg. Where is delta r? Tangent. Here, where is Fg? Down. Where is Fr? Tangent, horizontal. Now, look at the angle. This is the first angle. This is the second. This is the third. Is the angle between Fg and delta r constant or changing? So can you calculate the work when the angle is changing? No. Because at each point, you have an angle different from the other. So alpha here is not constant, it's variable. So I cannot. But don't worry, we learned something called conservative forces. Didn't we? We said that we have two types of forces, conservative and non-conservative. Force of gravity is conservative or non-conservative? And conservative force, the work done by a conservative force, depends on the path or it doesn't? Okay? So don't take this path. It's very hard to calculate. Take an easy path from 1 to... What is the easy path for gravity? This one is hard as well. So from here, if I draw it, wait, I want to remind you of what we did. This is number 2. This is number 1, and this is the path number 1, arc. It's not easy to calculate the work, yes, of gravity. Uzair, yeah? He said, let's take this path. Straight, yeah? Okay, for this path, Fg is this way, yeah? Delta R. So what do you need? This angle, yeah? Do you know this angle? So this is not a good strategy. Why you didn't take the path we talked about for force of gravity? Why you don't go horizontally and then vertically? You know that when you move horizontally, how much is the work of gravity? 0. Because work of gravity depends on height. It doesn't depend on horizontal distance. So this is not counted. What is counted? Down. So it means now the block is here. Fg is down. Delta y, down. What's the angle between them? 0. So how much is the work of gravity? You say Fg delta y cosine 0 when you're going down. And this is equal to change in kinetic energy, K final minus K initial. What is known here? The question says released from here, released. So kinetic 1 is 0. Kinetic 2 is half mv2 square equal fg mg delta y multiplied by 1, yeah? Do you need the mass? No. Cancel from both sides. Now, what is the unknown here? Delta y only, because V2 is given in the question. What is V2 in the question? What was it? 4? 4 meters per second, yeah? Yeah, at the lowest. At the lowest. 4. So we have 4 square over 2, because V square over 2 equal delta y, yeah? So how much is delta y? 16 over 2, which is 8, yeah? I forgot the g. It's always easy to forget the g. So delta y is 2 multiplied by 9.8, yeah? So say nearly is 10, nearly 10. 16 over 10 is nearly 1 point. Okay, meters. This is 10, 20 over 2. So it's 0.8, yeah? Nearly. Don't forget, what was the question? Find theta max. To find theta max, what do you need? H and L is 2. The problem was H. To find H, what do you need? L and? L is? Y was the problem, yes? Did we find Y or not? Point? So find H. When you find H, substitute here. All right? You see, using the technique of chapter 7 is not easy for the pendulum. I just explained it, but now we'll solve the same question by technique of chapter 8. All right? But just to remind you, on the sheet, question 27, it's a pendulum. But what's the difference? This time, the pendulum, it doesn't reach maximum theta, no. It says 0.8 kilogram object tied to the end of 2 meter string, swing as a pendulum. At the lowest point of its swing, the object has a kinetic energy of 10 joules. Determine the speed of the object at the instant when the string makes an angle of 50 with the vertical. Which means theta is not max. And the velocity here is not 0. You have kinetic one, yeah? But the question is opposite. If the angle is known and the length is known, what you calculate? H. And if you know H and the length, you find? And if you know Y, here you can find V. It's the opposite. You go in reverse. Right. Now we move to chapter 8. But I'll use this as an example. How to find it. So I'll solve a question 27, which I already did here, by the technique of chapter 8. So it's the same question. But look at the beauty of chapter 8. What did we learn in chapter 8? We don't need it. It's the same question, question 27. But using chapter 8 technique. Chapter 8 is about conservation of energy. Let me summarize what we did in 8. We said we have two systems. Either the system is conservative system or non-conservative system. If the system is conservative, it means initial mechanical energy equal final mechanical energy. Yes? which means potential initial plus kinetic initial must equal potential final plus kinetic. This is for conservative system. Now, for non-conservative, we have another equation, yeah? But let's concentrate on the conservative system now, yeah? If you have a conservative, how do you know your system is conservative? If you don't have friction and you do not have applied forces, yeah? Now, the pendulum question. Do we have friction?
No.
Applied force? No. Ft, remember, its work is 0, yeah? So, is the pendulum system conservative or non-conservative? So from now on, any questions of pendulum, it's a conservative system, which means your equation is ui plus ki equal uf plus kf. Let's apply it here. Let me remove all the extras here. It's the same question. So the pendulum is 2 meters. We want theta max. And the mass is 0.8. The length is 2 meters. Okay, this was 26, yeah? I can change it to 27, doesn't matter. 20.6, sorry. This is question 26. Length is 2, object, and V at point 2, lowest point is 4 meter per second. Find theta max. When you want to use the technique of chapter 8, it's very important you put the reference for energy, U, at the lowest point. So where do you have U level? At point 2. This is the ground, yeah? Like the ground? The reference level. So how much is U at 2? Now, if the reference is on 2, what is the potential energy at 2? 0, because it's the reference. At reference, the potential energy is 0. Why? Potential energy needs height, yes? So if you are on the point, 0. Now here, what do I have? I say U1, kinetic at 1, must equal U at 2, kinetic at 2. U for gravity, what's the formula? mg y at 1. Y is the height from the point to the reference, plus kinetic half m v square at 1. Here, mg y at 2 plus half m v square at 2. You can see when you have a conservative system, you do not need the mass. It's common in all 4. So don't look for the mass in the question. You don't need it, if this is the case. Now, where is the reference we said? At point 2. So it means all this is what? 0, reference. So this is 0. What else? And this question says at point 1, theta is? So how much is the kinetic energy here? So K1 is 0 as well. What is left? mgy1 and half mv. Of course, the m, we said we don't need it. So v to 4 meters, yeah? Per second. So what you calculate y1, yeah? y1 is 4 square over 2 multiplied by 9.8. The one we found a moment ago, yeah? You said nearly 0.6 meters, yeah? Now, where is y1 here? This is 0.1. From the point to the reference, vertical. This is y1. Remember, y1 means the y here. So if you know y, and you know L, you find what? H. So what is H equal to? L minus Y, 1 here. 2 minus 0.6, yeah? 1.4. Let's see.
0.8. Because 16 over 20.
Where is 16? What are you talking?
This
This is
is
0.8?
Yeah.
Ah, sorry. 1.2. This is H. Now, what is cosine theta max now? H over L, yeah? H is 1.2, L is 2, and you say cosine inverse, it gives you theta max. You got the answer, yeah? You should get the same answer. Y is the vertical height between the point and the reference. Where did I put the reference? At level 2, yes? Vertical, not horizontal, not at an angle, vertical. Right? Let's take another question. Now this is from 8. I'll take some of your break. I don't want to stop here because 8. Review of 8, yeah? Question 8. Question number 3. Question number 3. What do you see, question number 3? A projectile motion. Can you see projectile motion? Okay. Now, if you have a projectile motion question and you want to use the technique of chapter 8, the system is conservative. Why? There is no air resistance, no friction, no applied forces. Remember that. A question of projectile, conservative. What's the question here? 0.04 kilogram ball is thrown from the top of a 30-meter tall building from point A at an unknown angle. As shown in the figure, the ball attains a maximum height of 10 meters above the top of the building before it strikes the ground B. If the air resistance is negligible, what is the value of the kinetic energy of the ball at B minus the kinetic energy of the ball at A? Right. Let me draw it. A sketch. This is the ground. There is a building. You fire, initial velocity, it goes up and back. The height of the building is 30, and from here to there is 10, reached the maximum, and test the ground at point B, and fired at point A at an unknown angle theta naught. Remember, when we did these questions before projectile, we used the equations of projectile, all this. You see here, it's so easy. If I ask you, what's the speed when it hits the ground before? What you did? You had to find Vx, Vy, and then V, yes? Component? Now see here. We can find the speed here without doing all these vectors, using the concept of energy. Right. Conservative or non-conservative? Conservative. If it's conservative, I can say potential at A plus kinetic at A must equal potential at B plus kinetic at, yes? At any 2 points. Give me a reference now. Where do you put the reference? Okay, take it as a rule. Always take the lowest. Then every y will be positive, not negative. So if this is the reference, what is YA now? 30. What is YB? 0. So YB is 0, reference. YA is mgya. Kinetic at A half m v square at A. This is 0 and this is half m v square at B. Do you need the mass? Okay. I'm not answering the question. I'm saying something else here. The procedure. You write this. Now, the question doesn't need this step. The question says, what is kinetic B minus kinetic A equal to? This one. Don't open it up. This is A. This is what? So if I take this one to the side, what is left? UA equal KB minus, what is UA? MGYA. KB minus KA. M given in the question. G given. YA 30. That's it. Huh? What if you put the reference at A? What's the problem? YA will be 0. YB will be minus 30. Below the reference, yeah? So be careful of that. Next question. Let me give you a question which is a mixed, conservative and non-conservative. Yeah? Question 17. Question 17. Question 17 says, the figure below shows an object of mass m 1 kilogram starting from rest. It first slides a distance of 45 centimeters down a frictionless inclined surface and then slides across a rough horizontal surface whose coefficient of kinetic friction is 0.15. What is the maximum distance d traveled by the object across the horizontal surface? Okay. This is question 17. I'll do a sketch here. You have an inclined and then straight. You have an object here, a mass here. This inclined has an angle 20 degrees, yeah? And from here to there, 45 centimeters. Right. This block will slide and keep on moving up to a point here. And what happens? It stops. Why it stops? Because in this part you have friction. So here, rough friction. This part. But when it's sliding down from here to there, no friction. Frictionless. Right. This is a good question. Pay attention to it because it gives you a summary of chapter 8. Now this question, is it a conservative system or non-conservative? You can't say both. Both, it depends how you solve it. If you divide the question to two parts, so the part, let's say from point 1 to point 2, conservative, yes? No applied forces, no friction. From 2 to 3, non-conservative, yes? So this question now, it means we can do it this way, by part. Let's do it by part. 1 to 2, what? Conservative. So, and then 2 to 3, non-conservative. Now, 1 to 2, concentrate on 1 to 2. If you remember before, when you had an object on a slope, how hard it was to find the speed here because you used F net, forces, all this, yeah? Now we use the concept of energy. From 1 to 2, You said conservative. So what do I say? Kinetic at 1 plus potential at 1 must equal kinetic at 2 plus potential at, yes? Next, whenever you have potential energy, you have to give us the reference. Where is the reference? Ground. So where is the, here you need mgy, yes? 1. Here half mv1 square. Here half mv2 square. And here mgy at 2. Do you need the mass? Out. And all. But when we read the question, what was the speed here at 1 in the question? It says at rest. So all this is what? 0. Rest. What is left? mgy1. Where is y1? This is point 1, yes? Y is the vertical distance from the point to the level, yeah? So it's this. This is y1. Is it known or you have to calculate it? How? You have a triangle. 20, 45, y1. So you use sine. Sine 20 is y1 over 45, but change it to meters, yeah? So now you know y1. This side. When it reaches this point, do you know the speed? No. Unknown. So this is your unknown. How much is u2? 0, reference. So what is left from this equation? mgy1 equal half mv2 square. Of course, m with m is cancelled. So from here, what I'll find? v2. Yes? Now, v2 is the boundary between conservative and? So can now I use 2 with this side? Okay. From 2 to 3, conservative or non-conservative? Non-conservative. Good. Now, this is the first time we do a practice on non-conservative. What is the formula for non-conservative? Change in mechanical energy equal change in the potential energy plus change in kinetic energy. All right? How do you find delta E? Look on the formula sheet. What is delta E equal to in a non-conservative? It's work of friction force plus work of applied force. Delta U means U at 3 minus U at 2 plus kinetic 3 minus kinetic at 2. Now, this is a very important thing which you have to remember. Delta U for an object moving on a flat surface, how much is it? You are moving this way. Delta U need height or horizontal? So when you move this way, what's the change in height?
0.
So how much is delta U? 0. Object moving on a flat surface, it doesn't have change in potential energy. You need to go up and down. At the same level, there is no delta U. So here, this is 0. And this is 0. So what is left? WFR, WF equal kinetic final at 3. K3 is what? Because it stops, yes? Maximum. We need the maximum distance. 0. Kinetic initial, which is 2, half mv2 square. Okay. Now, didn't you find v2 from the first part?
Yeah.
Now we come to this side. Where is D here? Where is it? Inside work, yeah? What is WFR? Minus FR D. Do we have an applied force from 2 to 3? This is 0. Nowhere by force. equal half. Very good, minus. That's why this minus with this minus will cancel. Do you need the mass? No, because mass is inside the friction. Here, if I draw the block, this is Fg. This is N. This is what? Fr. Fg and N equal, yes? So how you find Fr? Fr is a mu N, and N is mg. So I replace Fr here. I say mu mg multiplied by d, half mv squared. Do I need the mass? No. Okay, V2 known, G known, mu given in the question. You find D. This is how you do this question. Now this question, just before I forget, from 2 to 3, you can solve it by the technique of Newton's law, F net. How much is F net here? FR only. So from 2 to 3, F net is FR, yeah? Delta what? It just happens here because there's no applied force. But here, F net is FR. What is F net? MA. FR, mu, mg, m with m. So what is A equal to? Mu g. You'll find A, yes? From 2 to? Okay. What is the initial velocity at 2? You found it from the first part, yeah? What is the final velocity at 3? 0. Linear motion, yeah? So what you say? V at 3 equal V at 2 plus AT. No, this is not useful. You need the distance. V square at 3. V square at 2 plus 2A delta x. Delta x is the x, D. V3 stops. V2, you found it in the first part. A, you found it from mu g. What is the unknown? But be careful here. The acceleration here must be negative because it's slowing down.
Shouldn't F net also be minus Fr?
We don't use vectors. F net equal Fr, yeah? But as a vector, it's minus. So look, I solved this part by chapter 5, review. And by chapter 2, motion. Yes? Stops, maximum distance. It says maximum, stops, yeah? Okay? Now, just one question, and I stop, if I can, because I don't want to stop while you have this problem. Let's just see this question. I give you a hint only, not that. So next time I see you, I can talk about it. Question 7 and 8, just look at them, 7 and 8. What do we have, 7 and 8? We have a skier skiing downhill or uphill. It doesn't matter. So let's look at 7, number 7. A skier weighing 800 Newton comes down a frictionless ski run that is circular, as shown. If her speed is 12 meters per second at point A, what is her speed at the bottom of the hill? I'll put the sketch here. I'll just give you a hint about it, and then you can leave. All right, look at the board. This is not circular motion. This is not a pendulum. It's a valley, a road like that. A skier here at point A is skiing down to the bottom of the hill, bottom of the valley. But because it's circular, so this is like radius, yeah? And from here to there is radius as well. What is this angle? 40. What's her speed at A? 12 meters per second, VA. What's the question? What's the speed at B? The system here is conservative or non-conservative? No friction, no applied forces, conservative. So what do you say? Ka plus u at A must equal Kb plus u at B. Where do you put the reference? At B. So what is UB? 0, reference. UA, you need this Y, YA. How you find YA? From the triangle. This is Y, this is H. Back to what we did for the pendulum. Similar to the pendulum, yes? Same. So what you need here? You need cosine 40 equal H over R this time, yes? How much is R in this question, in the diagram? 30 meters. So R, 30, H, cosine 40. So I'll find H, yes? If you know H, what is Y equal to? R minus H. R minus H gives you Y. Why we do this? Because you need Y where? YA. To the reference, yeah? So do this and then substitute. Kinetic at A is half mv square at A. Potential at A, mgya. And how you find Ya? Kinetic at B, half mv square at B. You don't need the mass. So be careful here. And the question says the weight. Weight means mg total. And in both cases, if you cancel m, you don't need it. You don't need the weight. So find VB. Yeah? This question and the question after is the same question, but it's a hill. So what you do here, put the reference here at A. So you need this Y. This is the angle. Thank you. I'll stop now.